Okay, so let's continue. Last time, if I remember correctly, we finished with the cohomological and homological functors. So today we're going to apply these ideas to prove the version of the 5 lemma in triangulated categories. So this is the following proposition. So let's call this 5 lemma for triangulated categories. And we suppose the following. Of course, we assume that we have a triangulated category. So if in a morphism of distinguished triangles, so the morphism as follows. We have one distinguished triangle with A, B, C. Then again, we have map to the A shifted by 1. And have another distinguished triangle, A prime, B prime, C prime, A prime shifted by 1. So we have maps. Let's call this first map from A to A prime F. The second map is G. So then there's a third map, which I'm going to call H. Of course, the last map we always have, this is just a shift of the map F. So if we have two distinguished triangles, we have a morphism between these two distinguished triangles. And if we assume that two of those morphisms are isomorphisms, then the same is true for the third one. So more specifically, I can say that if in a morphism F and G are isomorphisms, so then H is also an isomorphism. And of course, we can apply the rotation axiom, and again, it doesn't matter, do I start with F and G? Maybe I can start with G and H, then the next, and if G and H are isomorphisms, I can claim that the next map is also an isomorphism. So this is just one of the things that we can prove to have some specific statement with F and G. Okay, so that's the statement of the so-called 5 lemma for triangulated categories. What's the proof? Well, we can do the following. We take this diagram and apply the functor hom, where, well, that's a functor in the first argument, the contravariant functor. Maybe let's do the covariant version. So let's fix the first argument C prime, and then we can consider the covariant functor. But actually, we also need to consider the covariant. Also we need to consider the contravariant functor. We need both. So we start with this one, and the second option will be just an easy exercise. It's essentially the same argument. Okay. So we apply this. What we get? Well, we know that this is a homological functor, right? So we have two exact sequences and maps between them. Maybe I just continue this to the right. Doesn't matter, I can continue to the left, but I can decide to do this. I need a 5 lemma for the abelian categories, so I need 5 terms. So to do this, I continue and get C prime C. Then I have a map to the hom C prime A shifted by 1. And finally, the last term is hom between C prime and B shifted by 1. So then map F is inducing a map between homs. So I get a map to the hom between C prime and A prime. So let's call this map F with a low star. And of course, we also have a map G with a low star to the hom C prime, B prime, etc. I hope you can see what I wrote. So So here we have f shifted by 1 and then the lower star, right? And this is g shifted by 1 and then lower star. So I can say that, for example, f lower star is the functor home C prime and then f, right? So home with a fixed first argument is a functor, so there's an action on maps, and this f star is just by definition the result of the application of the home C star to the f, etc. So all other functors are defined by similar formulas. Okay, now we have a situation in abelian categories, and because we know that it is given to us in the statement that f and g are isomorphisms, so we can claim that f lower star, g lower star, and then f shifted by 1 lower star and g shifted by 1 lower star are isomorphisms, or in this case this is just abelian groups. So hence, by 5 lemma for abelian groups, H lower star is also an isomorphism of abelian groups. Right, so it means that, for example, if I choose the identity between C star and C star, it comes from some map phi, which is a map between C star and C. So I can say that the identity, I find it very convenient to, instead of the identity, write just one symbol, say 1. I think I'm going to write 1 instead of identity to the rest of the course. So identity on C star or 1 on C star, this is H lower star applied to some phi. Right? But what H star is doing with this phi? Well, this is just a composition by definition of the H star. So this is a composition of the H. Okay, so this is half of the proof. We see that there is a map phi, which is, if you compose this with H, you get identity on C prime. But you can believe me, we can check this later. If you do the same construction, but with the home where the second argument is fixed, so do this with the home where we fix the second argument, C prime, and then essentially the same argument with the 5 lemma for abelian groups give you but I think in this case I need not C prime, I need C. So I need maps to this C. So the same argument tells you that there is, to do this and get map psi. So in this case map psi will be a map from C prime to C, such that now if you consider composition of psi and H, you get the identity or the map 1 on the C. But that's exactly what you need to show that H is an isomorphism. Right, so then phi is equal to the psi and is equal to the H inverse by the standard argument that you've seen, for example, when you first saw the definition of the left and right inverse. So that's all we need. Okay, so now I have a couple of remarks. Quite trivial, but still important.
It's the very last step. So we have found the left and the right inverse.
Mhm.
And the lemma is that for homomorphism, has both left and right inverse at the same time. Yes.
I mean, no. The last step, this step is something completely trivial. It's something that you do in the first semester of algebra. So let me try this. You have psi, right? So where is psi living? So this is a map from C prime to C. So I can recompose this with the 1 on the C prime, right? And then for 1 of the C prime, I can write this formula. So psi, I compose this with H and compose this with phi. Then I use associativity. And this is 1. So this is 1 on C, composed is phi, this is just phi. That's what I meant by the argument from the first semester of algebra. Yeah. So several remarks. Okay, so we know that in the axiom TR1, any map, let's call this map F, say from A to B, can be completed to a distinguished triangle. That's the statement of the axiom. So the distinguished triangle is A, B, C. So this is F. Probably the names of the other maps is not important. So what I want to say is that now suppose you have, well, this is given in the axiom, right? So there's nothing new here. But suppose you have two such completions. So if you try to do this in two different ways, you'll get another distinguished triangle, right? But here you just can take, say, 1 on A, this is 1 on B. So identity maps are clearly isomorphisms. So it means that, first of all, by one of the axioms, I can find the map with, say, H, going from C to C prime. And by the 5 lemma, I can claim that this H is actually an isomorphism. So H is an isomorphism. And it means that C is unique up to isomorphism. You don't need to claim this in the axiom. We can just derive this using some ideas. So using 5 lemma and 5 lemma we can derive using homological functors. Yeah. Yeah, so far we haven't used the octahedral axiom. So this is still true for pre-triangulated categories. So the second remark, which is even simpler. So every distinguished triangle is determined, of course, up to isomorphism of all the objects in the distinguished triangle. So is determined by any of its maps. I think this is trivial. And the last remark is the following. So a special case of the second remark. So in particular, in the octahedral axiom TR4, the data is determined, again, up to isomorphism, as before, just by the two maps U and V. So we have A, B, C objects and two maps U and V. So this little remark, just a special case of the second remark, allows you to make more sense about this analogy with the third isomorphism theorem. Okay, now I want to formulate two exercises. So I formulate these exercises after the 5 lemma, so maybe 5 lemma could be helpful when you try to solve these exercises. So first exercise is the following. Suppose you have a distinguished triangle. So if A, B, and C with the map F from A to B is a distinguished triangle, so let me change this a little bit. So I want to fix this distinguished triangle and formulate two questions about this distinguished triangle. So this is a distinguished triangle. So then the first statement that I ask you to prove is the following, that F is an isomorphism if and only if the object C is isomorphic to the zero object. But we know that all our triangulated categories are additive categories, and in the additive category we have zero object, which is just by definition initial and terminal object at the same time. And the second exercise is the following. So suppose so let me say this like this. So map from C to A shifted by 1 is a zero map if and only if object B is isomorphic to the sum of the two objects A plus C. So in one direction, this is of course a trivial observation. If you start with the B, which is a direct sum or byproduct, to say more correctly, then this is not so hard to show. So this interesting statement is in the other direction. Okay. So at the moment we have definitions of triangulated category, and we have some quite elementary properties of triangulated categories. So the next step is to define what's a map between triangulated categories. So what additional requirements from the functor we're supposed to have when we have a functor between triangulated categories. And then we're going to discuss something like what's a subcategory and what's a quotient category when we discuss triangulated categories. Exact functors. Definition. An additive functor, so let's call this F, between two triangulated categories C and C prime is called exact, or sometimes as a complete synonym people say not exact but triangulated. It's called exact if we have the following two conditions. So the first condition is that actually this functor commutes with a shift. So if I take functor F precompose this functor with a shift. Now this t is a shift in the category t. So now it's again convenient, instead of the brackets and 1, use our notation t for the shift functors. So this thing is isomorphic as a functor to the postcomposition of the t on the category t prime with the functor f. So it commutes with the shift. And of course the second property you can guess. It's supposed to map distinguished triangles to distinguished triangles. So let me say that any distinguished triangle, say with A, B, and C, in the category T, is mapped by the functor f to a new distinguished triangle in the category T prime. So here I have f of A, which is mapped to the f of B, f of C. Now I have f of the A shifted by 1. But I also know by the first property that I can commute the shifts. So I can write that this is isomorphic to the f of A, and only then I apply the shift. So this last isomorphism is just 1 for first property. Okay, I guess that's a quite natural definition. And let's now prove one interesting statement about exact functors. So let f from t to t prime be an exact functor. Again, between two categories t and t prime, so as before. So t and t prime are triangulated. Now if h going in the other direction from t prime to t is the right adjoint, functor. So there is a very short convenient notation for this. Instead of writing that h is the right adjoint to the functor f, I prefer to write something like this. So h is the right adjoint to f, can be in some short notation written with this symbol. I'm not completely sure how to pronounce this symbol, so I'll write something like this and say that h is the right adjoint to the f. Okay, so if h is the right adjoint functor, then h is exact. And also, of course, there is a version not for the right adjoint, but for the left adjoint. So if I have left adjoint, now let me use the short notation. So left adjoint to the f. So now f is the right adjoint. So if I have this, then G is exact. Okay, proof. So to check that H is exact, we need to check those two properties. So let's start with the first property. So I take two objects, A and B, and just do the computation for the adjoint functors. I start with the home between A, then I have H of T prime of B. So the first step is to use the fact that H is the right adjoint. So in terms of the home abelian groups, it means that this is isomorphic to the abelian group, where I move this H from the right to the left. So this will be f of A. And then I have T prime applied to B. So this isomorphism is just by the adjunction. maybe I just want specifically indicate where I take my objects. So I take A. So A is living where in T. So this is for any A in T, and for any B in the T prime, I think. Yeah. I have this isomorphism. And if you want to be even more specific, I can write that this is home in the category T, and this second home is in the category T prime. But I'm not going to write the subscripts later, so if you want, you can figure out what I need to, in which category computing the home. Okay, so this is the first isomorphism. Now I want to move this T prime also from the right to the left. And I claim this is the following. This is the home. Now I have T prime inverse applied to the F of A. And the second argument is now just B. Well, why this isomorphism is true? Well, this is because T prime is an equivalence, right? And if you have an equivalence, then the right and the left adjoint to the equivalence is just inverse of this equivalence. Now the next step is actually that I can commute this T prime inverse and F. So I can require that in the definition that I can only commute with the T, but if this is true, I can actually commute with any integer power of T, because T is an equivalence. So now this thing is isomorphic to the home, and I write this as F applied to the T prime inverse A and A, and this is B. Okay, so now let's use the fact that H is right adjoint one more time. So this will be home between T prime inverse of A and I have H of B. Oh yeah, thank you. Yeah, so this is T. Okay, so, and finally, the last step is just to take this T inverse, use exactly the same argument that T is an equivalence of categories, and move it back to the right. So this is isomorphic to the home, A, T applied to the H of B. So now what we need to use is just apply the Ioannidis lemma. This is true for any object A and any object B also. By Ioannidis lemma, I want to conclude that I have what I want, that H composed with the T prime as a functor is isomorphic to the T composed with H. Well, this only shows that the first property of the definition is correct. We still need to show that the second property is correct. So for this, let's take a distinguished triangle. So let A, B, C, A shifted by 1 be a distinguished triangle in T. Hmm? Oh, do you know the statement of the Ioannidis lemma? So if you have two objects, right? And you know that if you consider the functors corresponding to these two objects, now objects being these two objects applied to B. So the functors are isomorphic. And it means that the object, when I apply this to B, will be isomorphic for any B. So then these two functors has to be isomorphic. Okay, so now let's take a distinguished triangle in T and show that when we apply functor H to this distinguished triangle, we still get a distinguished triangle. And I think that's the interesting part of the proof. So the first part is kind of straightforward. So if I try to apply H to this distinguished triangle, at least I'll get something like this, right? So I can apply H to A and get something, H to B, get something, and there is a map. I cannot claim that I immediately get a distinguished triangle, but at least I can write that there is a completion of this map. So I can complete this and get a distinguished triangle with C0. Okay. So I'm taking only one map between these two objects, get something in the category T prime, and then complete this to the distinguished triangle. So this is completion to a distinguished triangle of the map between H of A and H of B. Okay, now I want to take this new distinguished triangle. So this is in the category T prime, and to this distinguished triangle I want to apply functor F. So let's apply F to, so let's call this star, distinguished triangle star. Okay, so I'm going to write some commutative diagram with two rows. So the first row is just the result of the application of F to the distinguished triangle that we just completed. So F is applied to the H of A. So then F is applied to the H of B. So then F is applied to C, 0. And finally we have F applied to the H of A and then shifted by 1. Now I use the map that exists always for two adjoint functors. Remember that if you have two adjoint functors, then you have a map from the composition of the A composed with H to the identity. So this is what I'm going to apply to get the second row, or to get all the maps to the second row. So here I'll get the map to the A. Here I have a map to the B. And since this is a functorial, this is just a map of functors, so this is factorial, so this square is commutative. And finally I'll get a map to the C. Right, so these two maps I know because I have two adjoint functors. I know that this square is commutative. By one of the axioms for triangulate categories, you can complete this to the map of two distinguished triangles. So this is why this map psi exists. So get a map like this. Yeah, so this thing exists by TR3. And now I need even larger diagram with 3 rows to finish the proof. Okay, so in the next diagram, I start with the distinguished triangle with h of A mapped to the h of B. Then there is a map to the C0. So now I want to use another map of functors. If I compose f and h in the other order, I'll get the map from the identity. So there is a map from the identity functor to the composition of the h and f. So this allows me to construct 3 more arrows. So this will be the map to the h, f, h, and this is applied to A. Now I have h, f, h applied to B. Right, so there is a map like this, the vertical maps. Well, and finally there is a map from C0 to the h composed with f of C0. So this is from this unit of the adjunction. And now also we need, now we need to take the previous diagram, apply to this diagram functor h, and then I'll get the map from the second row to the third row will be the h of A, then h of B, and h of C. Okay, so I have 2 steps here. So this first part, the map between the first row and the second row, is coming from this map of functors that I have because I have adjoint functors. This gives me the upper half of the diagram. And the lower half of the diagram is exactly the diagram as before, where I applied functor h. So this is a hint that this is the same diagram. This is h of C. What is distinguished triangle? This one? I don't claim this is distinguished triangle. I only claim that this thing is distinguished triangle. Is this a distinguished triangle? We don't know, and we also don't know this, because suppose we know that this is distinguished triangle, this in the bottom row, then we can easily finish the proofs, right? The proof, right? What are these 2 vertical dotted arrows? Yeah. So this is the, again, I'm going to just write 1. Again, this follows because we have 2 adjoint functors. So if we, for some reasons, know this is distinguished triangle, then we can claim by the 5 lemma this is an isomorphism. That's what we want to show, right? But that's not the case because we don't know this is distinguished triangle. So that would be a mistake. So actually we want to show that this is an isomorphism by some other means. And if this is an isomorphism, actually it means that the triangle that we started with is the triangle that we want, right? Instead of the C0, I can write h of C. That's my goal. So somehow I need to show that this composition of these 2 maps give me an isomorphism. And this is done by the following step. So for any object A0, the sequence where I have home between A0, h of B, which is mapped to the home A0, h of C, and this is mapped to the home A0 H of A shifted by 1. So this sequence is exact. So how I can show that this sequence is exact? Yeah. So it's not clear that as it's written this is exact, but if I use just the adjunction and write that this is a home f of the A0, right? Applied to be the second term is the home of the f of A0, and then and I see that this sequence is isomorphic to another sequence, which is exact because we have a now this is a homological functor applied to a distinguished triangle, well, rotated distinguished triangle. So this is exact. By the adjunction. And now I use the same trick as before. If I know that this sequence is exact, right, so where I apply some, when I choose some A0 and apply home A0 something to this part, I get a, say, long exact sequence, and I also have the long exact sequence for the first row because it's distinguished triangle. I can use again the 5 lemma for abelian groups to conclude that I have home between A0 and C0 is isomorphic to the home A0 H of C. This is done by applying the functor home A0 with comma something to the first row and the third row of the previous diagram and using the 5 lemma. But now again we can just apply Ioannidis lemma. This is true for any object A0. So by Ioannidis lemma we get what we want. C0 is isomorphic to the H of C. Okay, so this finishes the proof. Do you have any questions before I erase something? Okay, so that's all actually I want to say at the moment about the exact functors. We're probably going to prove something about exact functors later. Now I want to define homotopy pullbacks and pushouts in triangulated categories. So homotopy pullbacks and pushouts. So let's do pushouts and the pullbacks will be exercise. Oh, let me just briefly remind you what a pushout is. So you take any category, you consider a diagram like this. You have some object y. This is mapped to the object z. There's also another map to the object y prime. And then if we can complete this diagram with two maps, f and g, to a square, such that this square will be universal in the sense that I'm going to describe in a minute, then this will be a coproduct or pushout. Right, so you start with f and g, you complete this to a square, and the square is supposed to be universal property in the sense that if you take any other commutative square, so I have maps like this, then there is a map making these two triangles commutative. Well, that's not what we're going to generalize. There is another point of view on this push out. I can write the following diagram. I start with the y, then I have two maps, g and f, mapping to the coproduct of z and y prime. And then I need to take the co-equalizer of this diagram, and this will be the map to the push out. Okay, so you can define using this diagram, or you can say that this is a co-equalizer of this diagram. And this is exactly what we want to generalize, right? If you work in the abelian category, or actually abelian is not needed, you can take additive. So in additive category, you can write, instead of these two maps, you can write the difference f minus g. So then here you have sum, and the kernel of this is exactly what we want. So you can consider this blackboard as a motivation for the definition. So we can understand the homotopy push out using the core kernel. And remember, there was an idea that when we complete the diagram in 10th grade category, this new object, say you start with A and B, you get new object C, we can think about C as a core kernel. So this is what we want to do in the definition. So I want to replace this core kernel by taking the third object in the distinguished triangle. So definition. So the homotopy push out of the diagram as before, but now this is in the triangulated category. So I have y, which is mapped to the z with the map f, and y is mapped to the y prime with the map g. So the homotopy push out, say, of this diagram in a triangulated category is some object z prime in the distinguished triangle of the following form. So I start with y. From y to the sum of y prime and z, I have a map with components g and minus f. That corresponds to the difference f minus g. So I have a map in the triangulated category, so I can complete this map to a distinguished triangle. So whatever object I get here, I'm going to call z prime, and this is by definition the homotopy push out of this diagram. So z prime that I can get here is by definition what I want. So remark. The homotopy push out is unique up to isomorphism. Well, that is because we already know that this third object in the completion of a map to a triangle is unique up to isomorphism. Okay. Now I want to understand, do I have a map? So what about the map that we have on this diagram? Do we have this map with our definition with triangulated categories? Okay, so I have objects as before, y, z, y prime. Now I have two maps, so this is f, this is g. F prime and g prime are two maps that we have in the triangle, right? Because we have a map from a direct sum, so it means that we actually have two maps, f prime and g prime. So on this diagram, I can write these maps. Oh, I guess this will be f prime and g prime, like this. Okay. Now suppose we have just some commutative square with some new object p. Can we construct a map from the z prime to p? Well, actually, again, to do this, we can use some ideas about homological and cohomological functors. So first of all, if I consider a diagram like this, so I have a map from y to the sum of y prime plus z, and this mapping components are given by, with g and minus f, and then let's call this map phi. So this will be a map corresponding to these two arrows on the diagram. So these two arrows together give me some map phi to the object p. So this is p, not d. Well, clearly the commutativity of this square with the object p means that this composition is 0. It's something like taking this map minus this map, so 0, because the maps are the same, the square is commutative. And now I claim that if I consider hom between z prime and p, which is mapped to the hom between y prime plus z p, and this is mapped to the hom y and p. Right, so in other words, I'm just applying the functor hom blank p to the distinguished triangle with y, the sum of z and y prime and z prime. So I get this exact sequence. And I have map phi living in the middle. And the fact that this composition is 0 tells me that in this exact sequence, phi is mapped to the 0. So it means that there is a lift, right? So there is some map, say psi, which is mapped to the phi living in the hom z prime p. But that's exactly the map that I want to construct. So from the homotopy push out, there's always a map psi to any p such that this outer square is commutative. Of course, the problem is that this map is not unique. Okay. Definition. Now I need to repeat this story not for homotopy pushouts, but for homotopy pullbacks. So the homotopy pullback of the diagram now have y prime mapped to the z prime, and there's also a map from z to the z prime. So the first map is called f prime, and the second map is g prime. So what's the homotopy pullback of this diagram? So this is y in the distinguished triangle of the form. So I have y prime plus z, and this is mapped using f prime and g prime to the object z prime. I know that I can complete this square but let me call the object that I want to write here, well, because I have an auto equivalence, instead of writing just some C and maybe writing C minus 1 that is mapped here, well, from the beginning I want to call this object C to be y shifted by 1. Then instead of this shifted by minus 1, I can just write y. Right, so this C is just a temporary notation, just to explain why I can write y here and y shifted by 1 here. So maybe I don't need this. So this is actually y shifted by 1, and this is y. So you start with the diagram, you get a map like this, you complete this to a distinguished triangle, but you just give a name to this thing to be y shifted by 1. So then this y is something like a kernel of this diagram. So that's again the main motivation why we want to define the homotopy pullback like this. Okay, remark. A commutative square that we already considered twice right, so the condition that this square is homotopy pullback and homotopy push out is actually the same condition. It's an exactness of some triangle. So in triangulated category, being Cartesian or co-Cartesian is actually the same condition. Is homotopy Cartesian or co-Cartesian if and only if we have a distinguished triangle like this. So why we need this homotopy pullbacks and pushouts? Well, first of all, that is just because we can define them. I think it's quite interesting that we have this idea using the completion of the triangle as an analog of taking kernels and co-kernels, and thus we can use this idea to define homotopy pushouts and pullbacks. But maybe let me formulate this as an exercise. Our first exercise is to define all homotopy all homotopy limits and colimits. Right? You know that you can present any limit and colimit using products and coproducts, kernels and co-kernels. Clearly, you can generalize this to the triangulated categories, but instead of the limits and colimits, you get homotopy limits and colimits. Just a little exercise to think about. And the second exercise is more important. Actually, going to need this later, so I suggest you try to solve this. So suppose we have a Cartesian square as before. So this is a Cartesian square. Now we do the following. We take a map, so for example G, but we can do this also for F. So let's take G. And let's complete this map to a distinguished triangle. So if you have this, there is another distinguished triangle. Now let me call map from Z to Z prime H. So the distinguished triangle will be with Z, Z prime. And the claim is that in this new distinguished triangle, the third object is the same as before, Y double prime. So if there is one distinguished triangle, well, essentially this is just notation, right? So notation for the Y double prime. So then there is distinguished triangle as above. And also there is a map between these two distinguished triangles. Okay. Next, we're going to define what's the triangulated subcategory. Now, there are two ways to define them. So I'm going to formulate one as a definition, and the second way will be quite kind of easy exercise. So let T be a triangulated category. A full additive subcategory say S in T is called triangulated subcategory if you have again several conditions. So condition 0, if any object isomorphic to an object in S is in S. So it is closed under isomorphisms. So the first non-trivial condition is that S is invariant with respect to the translation functor. So maybe I can write this just shortly. T applied to S is again S. So shift of any object in S is again in S. And the last condition, so if we have any distinguished triangle so if this is distinguished triangle in T with two objects x and y being objects in S, then the last object Z is also in S. Of course, again, applying the rotation, it's not important that I take this x and y. I can take y and z and claim that x is in S and so on. So this is one very specific way to define a triangulated subcategory. Well, remark, / exercise, S, so full subcategory, full subcategory S is a triangulated subcategory if S is triangulated. Right, so there's an independent triangulated structure on S, and also the embedding functor is an exact functor. So this I is the embedding. Okay, so another definition, more not really definition, but more notation. So if S is a triangulated subcategory, of T, we associate with this S a set of morphisms. So morphisms of C, there are two notations. I can use S as a kind of as a subscript, or I can say that this is morphisms of S. It's exactly the same two things. And this is by definition all the morphisms in the category T. So all the F, X to Y, well this is just an arrow in T, such that if I take this map and complete this map to a distinct triangle, I have the property that the object Z is in the subcategory S. So why this thing is important? Well, what's our main goal, say, for the next lecture, maybe for the next two lectures? We want to define the so-called Verdier quotients of triangulated categories, or just quotients of triangulated categories. And the famous derived category of an abelian category will be just an example of such Verdier quotient. And to define these Verdier quotients, we actually later going to need the homotopy pullbacks. That's the reason why I defined them. And we're also going to need this class of morphisms. There will be 2 points of view to how to look at the quotient. You can say that you want to construct a category such that all these objects in the subcategory are zero objects, right? But it's also the same as saying that all the maps that we have here become isomorphisms in the quotient category. Just 2 points of view on the same object. So this is why this association with the subcategory, this class of objects is important. Later we're going to see why these morphisms of S are important when we consider quotients or localizations. Okay, but now I want to show one quite elementary property. So proposition, but it's really, really simple. So every isomorphism is in the morphisms of S, and this is true for any triangulated subcategory. So for any triangulated subcategory S. The proof immediately follows from the exercise that I formulated today. So this is an isomorphism if and only if we have a distinguished triangle like this, with a zero object. Right? But the next observation that 0 is in any triangulated subcategory because this is an additive subcategory. An additive subcategory contains the 0 object. So this immediately follows from the exercise. Yeah, and in this course there will be 4 assignments, and the exercises that I've just formulated today, I think all of them will be in the first assignment. So the first assignment will be posted next week, but if you can start solving the exercises today if you want. So in particular, this property you will prove in the first assignment. I mean, that this is an isomorphism if and only if this thing is a 0 object. Okay, next proposition, which is a little bit more interesting, but still quite easy to prove. Do I have time to do this? I still have 5 minutes. I think 5 minutes is enough to prove this statement. So let F be a map from X to Y. G is a map from Y to some Y double prime. So these are 2 maps in the category T. So if any 2 of the F, G, or the composition G and F lie in the morphisms of S for some subcategory, triangulated subcategory S, then so does the third. Right, so consider 3 morphisms, F, G, and the composition. If for any 2 you know that they are in the morphisms of S, then the same is true for the last one. No. So the proof immediately follows from the octahedral axiom. So this is probably the first time when we really need triangulated categories. So the octahedral axiom tells us that we have the following huge diagram. So essentially I'm just copying the diagram from the axiom, but with the notation that I have in this proposition. So I hope that this is correct. You can try to check this. Now, if we just look at this diagram, we can see the following, that F is in the morphisms of S. And so we have F here. So this is the morphisms of F of S if and only if Z is an object in S. Now, what about the composition? G composed with F. So when this is a morphism in S. So look at the second distinguished triangle, the second row. This happens if and only if Z prime is in S, right? As follows from the second row. And finally, we need G. And for G, we're going to use the second column. So G is the morphisms of S, if and only if Y double prime is in the S. But now we also know from the octahedral axiom that the third column is also a distinguished triangle. If you know that the two objects in this distinguished triangle are in S, then the third object also in S. That's the definition of a triangulate subcategory. I think that's all we need to finish the proof. Okay, so I want to finish today's lecture, and the plan for the next lecture is to define what's the quotient of a triangulate category by triangulate subcategory, the so-called Verdier quotient. And after this, if we can finish this next week, so in 2 weeks we're going to define derived categories and derived functors, and after this we're going to switch to algebraic geometry. So we finish this category theory preliminaries and do actual algebraic geometry.